Okay, all that remains now is to complete the design, and believe it or not, this is actually a problem that you're completely prepared to do, one that you have no additional information that you need to solve this problem. I just want to clarify that this table up here is extremely important to us. We put a lot of work into this table, but the only thing that really matters now is the first column, and it's hard to just highlight the first column, the present values, the present state, and then these last two columns, the j and k for the most significant bit and the j and the k for the least significant bit. Those are really the inputs and the outputs of the next state decoder. Let me just scroll back up to the beginning of the lesson and remind you this is what our circuit looks like. And the present state, these are the values of the Q. The next state decoder, its job is to generate the J's and the K's that go back into the present state, so that the next time it receives an active clock pulse, it will generate the next state. So we're trying to design the next state decoder, the combinational logic that accepts the Q's as the inputs and generates the J's and the K's as the outputs. But what we've got now is we have a table that shows the present state, these are the Q's, and the J's and the K's for each bit. All I'm going to do is I'm going to ignore these middle columns right here, and I'm going to expand the present state into two columns, one for the most significant bit, one for the least significant bit, and I'm going to split the J and the K columns. So I'll have 2 inputs and 4 outputs, and that's really what this table is doing right here. So the inputs are Q sub B and Q sub A, and the outputs are J sub B, K sub B, J sub A, and K sub A. It's traditional for the least significant bit to be referred to by the letter A, and then for succeedingly, increasingly significant bits to go up by letters of the alphabet. So in this case, we have only 2 bits. The most significant bit is Q sub B, and the least significant bit is Q sub A. So we have a system here. We need a system that has 2 inputs and generates 4 outputs. Well, we don't really have tools to do that, but we do have a tool that allows us to generate 1 output. And we're going to use that tool 4 times. So what I want to do right now is I just want to consider these first, gosh, I wish I could highlight just the columns. I want to consider just the 2 inputs and just this 1 column right here, this J sub B column. So I'm just going to generate J sub B. And I have a variety of different tools I could use to do that. Certainly I could just use Boolean algebra, but the tool that I like the best is Karnaugh Maps. So that's the one we're going to use. So just remember the pattern 0, 1, X, X. Because when I look down here into this Karnaugh map, which has Q sub B and Q sub A as the inputs, I fill it in with 0, 1, X, X. And because it's only a 2x2 Karnaugh map, I don't need to worry about the gray code reordering of the columns or anything like that. Everything is in order when you're in just a 2x2. So 0, 0, 1, 0, 1, X, X. And you can look at the numbering. 0, here, this is the first cell, the second cell, the third cell, and the 4th cell. So we even know what order to put the numbers in, 0, 1, X, X. And then I'm going to take the fewest groups and the largest groups possible. That covers all the 1s, doesn't cover any 0s, and I can cover X's if I want to, but I don't have to. Well, circling the bottom row here is the best way to cover all the 1s. There's just 1 to be covered. The largest group would pick up this X. The 0 up here is not covered, and the X doesn't need to be up here in cell number 2. So when I look at what's common about all of these cells, they all belong to the bottom row, which is where Q sub A is equal to 1. And since that's a 1 instead of a 0, then I see that the output is just going to be equal to Q sub A. So that's actually a very simple digital logic function. It's just a wire. I don't need to AND anything. I don't need to invert anything. I just take a wire. And so that makes our lives quite easy. I can then say, okay, I want to do the other columns, K sub B, J sub A, and K sub A. And so that's what I've done down here. So these are the other 3 inputs. You can see then that K sub B is going to actually have the same bottom row circled. Now it isn't the same patterns of 1s and 0s. You can see that here what's essential is that I cover cell number 3, and I'm allowed to cover cell number 1, whereas up here it was essential that I covered cell number 1, and I was allowed to cover cell number 3. Similarly, down here for J sub A and K sub A, both of these, I can just cover the entire thing. And if you cover the entire thing, you just say that it's equal to 1. So this is a very simple device because both J sub B and K sub B are going to get just Q sub A as their inputs, and J sub A and K sub A are both just going to get 1. So this is almost the simplest sort of next state decoder that I can imagine, and yet it yields very interesting behavior. It yields the behavior of a 2-bit counter, of a modulus 4 counter. The only thing that really remains then is to draw a circuit diagram. So the circuit diagram is going to be represented here. You can see now I have 2 flip-flops. I have to have 2 flip-flops to represent the two bits of the number. the Q sub B and Q sub B bar, Q sub A and Q sub A bar. I have the clock signal that's going to both of these devices. And let's see, J sub A and K sub A, they both get 1. So that's permanently tied to 5 volts. And then Q sub A is fed back into both J sub B and K sub B. Now, if you're really paying attention, you might recognize this circuit. This was the quote-unquote sequential digital circuit number 1 from our previous lab, where you had to analyze what this circuit was doing and figure out that it was, in fact, counting 0, 0, 0, 1, 1, 0, 1, 1. And so I have to admit to you now that in order to prepare that lab, I actually did the design process that we've just followed. So this is how you can, given a particular pattern of zeros and ones that you want to generate, you can just follow the design process that we've just learned and figure out what needs to be the values of J sub A, K sub A, J sub B, and K sub B. Of course, if you have more than 2 flip-flops, then you'll have more than 2 inputs. Up here, these Karnaugh maps are only 2 by 2. You could have one that would be 4 by 2. We'll see an example of that in just a minute. You could have one that would be 4 by 4. We aren't going to really do any 4 by 4 examples. That would be a lot more work. And there'll be more flip-flops. I'm sorry, there'll be more flip-flops, but that means there'll be more inputs. Notice that here there were 4 Karnaugh maps because I only had 2 flip-flops, each of which had 2 inputs. If I had 3 flip-flops, each of which had 2 inputs, that would mean 6 inputs total, 6 Karnaugh maps total. So in those cases, if we have to have 6 Karnaugh maps, well, that's going to be more work. But of course, you're designing a more complex system, and it isn't hard work. It's actually kind of almost fun to solve these problems. It's kind of like a little puzzle to see just how clever you can be. So that's all that there really is to it. You first of all figure out what is the next state based on the present state. Then you figure out exactly what transitions you need to see, what conditions would lead to those transitions, what flip-flop inputs would lead to those conditions, and then use the flip-flop input columns to figure out the Karnaugh maps to yield the hardware for the J's and the K's. So this gives you enough information to go ahead and do the designing the next state decoder example problem. And then after you finish that, then there's one more example problem where you do it from start to finish. So I wanted you to have the opportunity to see an entire design from start to finish in one example. That's the second example that you see right here.